Hi, this is Dan Beaulieu for iConnect 007. Today I'm at Prototron in Redmond, Washington talking to Mark Thompson, who is a customer support engineer here at Prototron. One of the things we're going to be talking about with Mark is impedance and everything you ever wanted to know about that subject. So Mark, thanks for being with me today.
Thanks for having me, Dan.
Well, let's start off right at the beginning. What is impedance?
Well, impedance is controlling energy through a trace and through substrate to get to a point where on the surface where you've got components mounted, you're meeting the exact constraint of energy that needs to go to that component. That's the simplest explanation.
Okay, so it's just a simple equation controlling the energy on the board.
Indeed it is.
And it's matching the components? Is that what it's really doing?
It's matching the speeds of the components.
Matching the speeds. So it's all about engineering and speeds and so on and so forth. And why is it so important?
Well, devices these days are predicated on having these impedances at the surface to be able to function properly. So if I have a number of devices that function at 50 ohms, 60 ohms, 75 ohms, 100 ohms, 90 ohms, 120 ohms, all of those things have to be well within 10%, and we need to make those work to be able to make the device work.
Okay. And you help your customer, how does it work? Your customer will send you data. It'll have a required impedance. Is that right way to say it? It'll have a required impedance, and you'll measure that to make sure it's all coming out right?
We actually have a number of different ways that it's being done. Since we are a fast turn and prototype, we have customers approach us at the point where they're doing the layout. So at the point where the engineer has come to them and said, these are the controlling parameters, this is the family of materials I want to build it on, these are the impedances I need, this is where they reside. Go to a fabricator, have the fabricator model those, give us the lines and spaces to meet those impedances, and have them provide us with a dielectric stack-up that's going to also meet those same impedances on the material that we're asking for. Okay,
so it really is a partnership between you and the customer, you the fabricator and the customer. Okay,
without a doubt.
That's insightful to me, because I really thought it was they knew what they were doing, they were sending it to you, and you were just verifying.
A lot of times they do, and a lot of times people take that tag, but you have to bear in mind there are some things that may be out of their control. Environmental conditions, press parameters, and variances in effective dielectric constants. Those three things combined can mean that if he's modeling at 4.5 at 1 meg, and the reality is that it's going to be something like a 3.3 dk at 20 meg, or 5 gig or something like that, then the dielectric constant is going to be just that much lower. What does that mean to a designer and engineer? Well, it means that if they design something at 0.1 millimeter lines and spaces, and all of a sudden their desired dielectric constant went from 4.5 to 3.3, it means that their lines are now going to have to grow exponentially. And with a 0.1 millimeter space, you don't have a whole lot of room to be able to do that.
Right, right. So what's happening here is sometimes they've got half of the equation, and they need you, the fabricator, to provide the other half, the verification, if you will.
Exactly.
Making sure it's going to work, and that's why it's there. I mean, because I know one of the things that happens, I work a lot with your salespeople. And one of the things that their complaints is, why is Mark taking so long? My competitors are getting this quote in 1 hour. Why is he taking so long? So let me ask you a couple of questions there. First one is, what is taking you so long? I'm sure it's not days, but why does it take you longer than an hour to do this?
Well, there's a couple of reasons for that. One, if they were all, say, for instance, 4, 6, 8-layer boards, and they were all 1 or 2 impedance scenarios per, I can bang those out in maybe 10, 15 minutes. Right. So it's a nominal turnaround. If it's a 16-layer board, a 26-layer board, and there are upwards of 30 unique impedance scenarios, it's going to take me exponentially longer to be able to do all of those scenarios. In conjunction with that, we're not just doing it based off any notes that may be off of that drawing. We're also going into the Gerber data and verifying that all of those exist. A lot of times we may be entering into the program at Rev B, Rev C, Rev D, and so some of those impedance that may be listed on the drawing aren't actually there. They don't exist at all. And so it's on our onus to verify not only that the impedances can be done, but also that they exist. And so that's why it can take a little bit longer.
And well, what about the other guy? How come he's doing it in an hour?
I would say that I would have to answer that he's not doing it. because doing due diligence would mean that he's actually looking at all of those layers as well as running all of his impedances. The calculations take virtually no time at all. It's an algorithm. You plug in the numbers and it gives you the solution. So that part's not really difficult at all. It's the coming up with the stack up. It's the verifying of every one of those impedances on every one of those layers to make sure that we are satisfying their impedances.
Okay, so somebody's taking what would take you 3 hours, 1 hour. Basically, they're just going with what the customer sent in.
I would have to venture to guess that that's exactly what's going on. They're looking at the drawing, they're only doing calculations based on that drawing, or worse, maybe only emulating a dielectric stack-up that may have been provided by the customer and not even running any impedances.
Wow. And what can happen? So what? So what if they're only doing that? What's going to happen?
Well, it could mean a huge mismatch. Depends on the material. You know, we talked about 4101/126 just a minute ago. There's a good 30 materials that fall into that category. And that being the case, it means that there's a whole slew of effective dielectric constants, a whole slew of loss tangents, and again, bringing in the other three things that I mentioned, environmental conditions, press parameters, and then you add those changes in dielectric constants, you could be talking about a huge mismatch. So we really encourage our customers to get with us as early as possible convenience to be able to run those numbers for them, to be able to give them good solutions. And bearing in mind, the goal for our customers is to give it to a fabricator at 10%. Don't try to take it further. Don't try to spec an exact type of material, an exact dielectric, or any of those kinds of things. Keep it semi-loose and you know, give us your intentions, tell us what it is that you need, and allow the fabricator to come up with the stack up. And
sounds in some ways like you're saving your customer from himself. I mean, you really are.
In a lot of cases, we do. When we talk about you know, taking up on a new revision, for instance, not only do sometimes those lines not exist, but now they've changed a reference plane scenario where it was previously a dual asymmetric, now it's turned into a standard strip line. And they may not have calculated that. They may not have taken that into consideration. So that's something that we're going to give them feedback on. Simple things like differential pairs. You know, there's two basic rules for differential pairs. They need to have a matched length, and they need to have a predicated space between the pairs throughout the run. So many times these days we see people having a 7 mil line with an 8 mil space, 5 mil space, 8.5 mil space, 9 mil space, all on the same run.
So what does that, I know what those numbers mean, but what does it mean for the board?
It means I wouldn't be able to control that. I would have no possibility of being able to control that trace at that juncture because there is no predicated same space throughout that particular run.
I know, to your credit, one of the things, like I said, you know, helping Protron with their sales, their marketing, is we get a lot of testimonials. We get a lot of testimonials giving you credit for helping them, the engineers, the designers, in this kind of thing. So I take it you communicate a lot with those people.
All the time. I'm not afraid to pick up the phone.
Yeah.
And we're also good at trying to propose solutions when we come up to something that's not maybe going to work for folks. Many years ago, we came up with a solution for decoupling using some very thin dielectrics for one of our bigger customers. And they were so pleased. We took a 14 layer down to an 8 layer, and now it's a legacy board. We build every revision of it. It's always the same dielectrics. And that's also beneficial from a fabrication standpoint because now we have a template for it. We not only have a stack-up template, but we have an impedance template for it. So every time a new iteration comes along, it takes us less and less time to turn that quote around. And so that can help in answering your question about quote response times.
So it's kind of like if you're serious about impedance on your boards, you better come to Prototron, talk to Mark Thompson, I would guess.
Absolutely right.
Yeah, okay. Mark, I really appreciate you spending the time clearing that up for us. I think it'll be useful to a lot of our people watching in. Thank you.
Thanks so much for your time.
Yeah. For iConnect 007, this is Dan Beaulieu saying thanks for watching.